In this video lesson, we will explore polynomial and rational inequalities. We have already studied inequalities. If you recall, we've learned about linear inequalities and how to write that solution set in interval notation and drawing a graph on a number line. We'll do some of those same things here. So specifically, we'll look at polynomial inequalities and rational inequalities. So a polynomial inequality is an inequality of the form f of x is greater than 0, f of x is less than 0, f of x is greater than or equal to 0, or f of x is less than or equal to 0, where f is a polynomial function. Some examples of polynomial inequalities are x squared minus x minus 6 is greater than 0, 2x cubed minus 18x is less than or equal to 0. X to the 4 minus 13x squared plus 36 is greater than or equal to 0. So recall we've worked with these types of expressions before, but we've had them as an equation that is equal to 0. And when we solved that equation f of x equals 0, we obtained the values of x that make that polynomial function 0. That is, we found the zeros of the polynomial function. So one thing that is interesting to note then is that at all other values of x, f of x will be either positive or negative. That is, greater than or less than 0. So remember that the zeros are what make the output 0. So at every other x value, the output will either be positive or negative. And so we're going to explore a graphical way to solve these inequalities as well as an algebraic method for solving the inequalities. And I have an example of a function, and all I want us to think about is where is this function 0, where is this function positive, and where is it negative. And so I have the function f of x equals x squared minus x minus 6 graphed on this slide. Notice that if we set x squared minus x minus 6 equal to 0, we can solve this quadratic equation by factoring to have x minus 3 times x plus 2 equals 0. Setting these factors to 0, we get that x minus 3 is equal to 0, or x plus 2 equals 0. So x is equal to 3 or x equals negative 2. So the 3 and the negative 2 are the x values that make this polynomial have an output of 0. And we see that graphically because at negative 2, 0, and at 3, 0, we have points on the graph. Right, those zeros correspond to the x-intercepts of the function. So notice that before and after a 0, the graph alternates between being above and below the x-axis. Notice that to the left of negative 2, 0, the graph is all above the x-axis. Well, what do we know about points above the x-axis? These points are specifically in quadrant 2, and we know that in quadrant 2, we have a negative input value but a positive output value. So that is, the y value is positive on these points on the graph. So the sign of y is positive to the left of this point, negative 2, 0. And then note that between the negative 2, 0 and the 3, 0, the part of the parabola goes down to its vertex and then it turns back up. But all of these points in this region are below the x-axis. Well, notice that these points are in quadrants 3 and 4. And in quadrants 3 and 4, we either have a negative input and a negative output, or a positive input and a negative output. In this part of the graph, the y value is negative. And then to the right of 3, 0, the graph goes up above the x-axis. All of these points are in quadrant 1. And what we know about quadrant 1 is that the points are positive, positive. So that is, these are x values for which the y value is positive. So notice that what I had said earlier is that at every other x value besides the zeros, the output will either be positive or negative. And the graph tells us in which regions we have positive and negative y values, because we know where it's above the x-axis, the y value is positive, and where the graph is below the x-axis, the y value is negative. Now we can extend this and do it algebraically rather than graphically. And so algebraically, we can determine the sign of a function by using test points. We first find the zeros of the function by solving the equation f of x equals 0. And I actually did that on the previous slide, and we found that 3 and negative 2 were those zeros. And so we place the negative 2 and 3 on a number line in order. And notice that the negative 2 and 3 subdivide the number line into 3 regions. I like to label these A, B, and C. So region A is everything to the left of negative 2. And as an interval, we write that as negative infinity, comma, negative 2. Region B is everything between negative 2 and 3. So in interval notation, that is parentheses negative 2, comma 3, close parentheses. And then region C is everything to the right of 3, which is in interval notation 3 to infinity. And remember that just like in the graph, that every point in one of those regions was all above or all below the axis, right? It only changed through those zeros. And so as a result, it is sufficient for us to test just one single value in each of these regions to know what the sign of f of x is. And so we can actually plug in a point in each of these intervals into the function to determine what its output value will be, either positive or negative. And so in region A, something to the left of negative 2, we can plug in negative 4. So if we plug in negative 4, we go to this function that is the thing that's opposite from 0. So our f of x is x squared minus x minus 6. So if we plug negative 4 into the function, we get negative 4 all squared minus a negative 4 minus 6. Which is 16 plus 4 minus 6, or 14. And what I really need to know from that is that that value is positive. So that tells me that in region A, every input value will have a positive output value. In region B, between negative 2 and 3, we can test the value of 0. 0 is the one I always recommend testing if it's in the region. When we plug 0 into the function, we get 0 squared minus 0 minus 6, which is just negative 6. So that tells me that for every value in interval B, the output of the function will be negative. And then in region C, something larger than 3. So I can choose 7. There's infinite number of possibilities. You can choose whichever number you want as long as it's in the interval. Plugging in 7, we get 7 squared minus 7 minus 6, which is 49 minus 7 minus 6, or 36. So because that input value has a positive output value, that tells me that every value in the interval C will have a positive output. The graph and the algebraic manipulation by testing points can help us solve inequalities. So for instance, if I have the function, like I've just stated, f of x equals x squared minus x minus 6, and I want to solve the inequality x squared minus x minus 6 is less than 0, then what this means is that I need to find all the x values for which f of x is negative. So graphically, that means where is the function below the x-axis? Algebraically, it meant which interval gave us a negative output value. And so we can confirm both with the graph and the chart that we just constructed that between the -2 and 3 is where the graph lies below the x-axis. So all the y values are negative there. Or using this test point of 0, we also found that we had a negative output value. And so the solution set for x squared minus x minus 6 is less than 0 is the interval from -2 to 3, open parentheses. Now, what about x squared minus x minus 6 is greater than 0? So that would tell us to look for all the x values for which f of x is positive. And so graphically, that means where is the graph above the x-axis? Algebraically, it means where do we get a positive output? Well, the graph was above the x-axis to the left of the -2 and to the right of 3. And so also we confirmed that in our table. We found that in interval A and C, we had a positive output value. And so the solution set would be from -infinity to -2, union 3 to infinity, with a parentheses on all of those endpoints. The only thing that changes when we have less than or equal to 0, so if I wanted to solve x squared minus x minus 6 is less than or equal to 0, that just means I need to also include the zeros of the function. So that is where the function is negative and 0. And so that means that we can then include those x-intercept values of -2 and 3. We would have bracket at -2, comma 3 bracket. In a similar fashion, x squared minus x minus 6 is greater than or equal to 0 would be where the graph is positive or also 0. And so we can include, again, those endpoints to have -infinity, comma, -2, bracket, union, bracket, 3 to infinity. And so the graph and the table actually give us a way to solve a polynomial inequality. We first want to rewrite the inequality so that one side of the inequality is 0. Then we will find the zeros of the function by solving the associated equation f of x equals 0. Those zeros are called boundary numbers. Then we're going to draw a number line, place those boundary numbers on it. Algebraically, we can test a point from each region formed by the boundary numbers in the inequality to see if the test point satisfies the inequality. We can also look at the graph to determine which test points satisfy the inequality. Then we will determine which intervals satisfy the inequality and determine if the zeros are included. And then we can draw the graph of the solution set and write the solution set in interval notation. So I have a few examples that we'll go through together. The first one is x squared plus 2x minus 15 is greater than 0. So this is a quadratic or polynomial inequality. And here I want to first find the zeros of this function. So if we think about f of x is equal to x squared plus 2x minus 15, I'm going to solve where x squared plus 2x minus 15 is equal to 0. We can do that by factoring. We get x plus 5 times x minus 3 equals 0. So setting each of these to 0, x plus 5 equals 0, or x minus 3 equals 0, we get the boundary numbers of -5 or 3. And so on a number line, we can place those two values of -5 and 3. And notice that this subdivides our number line into three regions we'll call A, B, and C. So the three intervals that we need to test, interval A is from -infinity to -5. Region B is from -5 to 3. And region C is everything to the right of 3, or 3 to infinity. Then we want to test a point in each of these regions. So a test point in region A is a number to the left of -5, so we'll call it -6. And then we're going to plug into the original inequality. Now actually we could look at what the sign of the function is and then determine if we need it to be positive or negative, because we are trying to find all values of x for which f of x is positive. So that is, what input values have a positive output value. So we can test it by plugging into the original inequality just to see if we get a true statement. If I plug in -6, I would have -6 quantity squared plus 2 times -6 minus 15. And I want to see, is this result a positive value, right? Is it greater than 0? This gives me 36 minus 12 minus 15. Is that greater than 0? Well, this is what, 24 minus 15, or 9, which is greater than 0. So this is true, right? So this is saying that that test point of -6 has a positive output value. A number between -5 and 3, I like to use 0, as I said before. So I'm going to plug in 0 to get 0 squared plus 2 times 0 minus 15. Is that greater than 0? Well, when we simplify, we get -15. Is that greater than 0? No, that is false. So region B is where our output value was negative. And then in region C, we can plug in something larger than 3. So I'll plug in 4. 4 squared plus 2 times 4 minus 15, is that greater than 0? So we get 16 plus 8 minus 15 is greater than 0. It's 24 minus 15, or 9, and that is greater than 0. So again, this is showing me that the 9 is a positive output value inside this interval C. So algebraically, we have just determined that the solutions of this inequality lie in regions A and region C. So I'm going to shade those on my number line to indicate that solutions are located there. Then I have to determine, are those endpoints included? Can I include the -5 and 3? And I cannot, because I'm looking for where this is strictly greater than 0 not equal. So I have to exclude those zeros by putting a parentheses to indicate that. So my solution set in interval notation is parentheses negative infinity to negative 5 parentheses union parentheses 3 to infinity. Now I've also included a snapshot of the table that I can obtain from the calculator. If I input the function x squared plus 2x minus 15 in my y1 and look at the table, notice that this gives me really what my output values are, if they're positive or negative. So if you didn't want to by hand do these calculations, you could use your calculator, right? If I found the test point of -6, well, my test point is -6, but the output value is 9. Is that greater than 0? So yes, that's true. Between -5 and 3, well, between -5 and 3, I see a lot of values here. All of those values are negative, right? So for -4, -3, -2, -1, 0, 1, 2, the output values are -7, -12, -15, -16, -15, -12, -7. So all of those y values are not greater than 0. Those are negative, so they would not satisfy the inequality. For the input value of 4 in region C, my output is 9, which is greater than 0. So again, the calculator can assist you in getting some of these results a little bit quicker. Now, another way that you could do that is just by using the graph of the function. And you don't even have to be very precise. If I think about the function as being f of x is equal to x squared plus 2x minus 15, and I find those zeros by setting the function equal to 0. We just found on the previous slide that -5 and 3 are the zeros. So if I put those on a number line, and think about my number line as being my x-axis. Well, I know that the graph is going to have a point at those two values on the x-axis because those correspond to the x-intercepts. And I also know that this polynomial function is a quadratic. The graph is a parabola. It has an even degree and a positive leading coefficient, which means that it's going to go up to the right and up to the left. So that means it's going to go up to the left of -5 and up to the right of 3, which means it will have to go down below the axis and then curve back up to come up through the 3. And so just having a rough idea of what the graph looks like, I can solve this because now I'm trying to find what intervals of x have an output that's positive. And that is, where is the graph above the x-axis? And that is, if you think about regions A, B, and C formed by those zeros, when region A it is above, in region B the graph is below, and in region C the graph is above. So that tells me right away that the solution set would be -infinity to -5 union 3 to infinity. Now, if you didn't want to rely on your graphing skills by hand, you can use a calculator. If I input x squared plus 2x minus 15 into the equation editor and graph it, notice that I get the same result. It is a parabola that opens up, going through -5, 0, and 3, 0. It's above to the left of -5, above to the right of 3, and then the graph is below between those two values. Another polynomial inequality that we'll do is -4x cubed minus 8x squared plus 4x plus 8 is less than or equal to 0. So this polynomial I need to solve by first replacing the inequality with an equal sign, that is to find those boundary numbers. So I'll set the function equal to 0 and solve. This is a polynomial with 4 terms. We can use grouping. When we pair together the first two and last two, we factor out the common factor. Between negative 4x cubed and negative 8x squared, there's a negative 4x squared in common. That leaves an x plus 2. And then plus 4x plus 8 has a plus 4 in common, which leaves in parentheses x plus 2. And then that is equal to 0. So now we see this common binomial of x plus 2 that we can factor out, which leaves a negative 4x squared plus 4 equals 0. So now it's factored. We can set x plus 2 equal to 0, or negative 4x squared plus 4 equal to 0. So we get x is equal to negative 2. We can use the square root property to solve the second equation. We can subtract 4 to get negative 4x squared equals negative 4, and then divide each side by negative 4 to get x squared equals 1. So by the square root property, x will equal plus or minus the square root of 1 or plus or minus 1. On our number line, we have 3 zeros to place. We have to put negative 2, negative 1, and 1. And now this forms 4 regions. We have region A, B, C, and D. So region A is everything to the left of negative 2. So negative infinity to negative 2. Region B is between the negative 2 and negative 1. So the interval negative 2, comma negative 1. In region C, we have the interval between negative 1 and 1. And region D is everything to the right of 1, which is 1 to infinity. So the test points that we can include, something to the left of negative 2 would be negative 3. In region B, that's going to be a little bit more tricky because there's not an integer between negative 2 and negative 1, so we need to include something like negative 1.5. Our test point in interval C, between negative 1 and 1, I would use 0. And in region D, something to the right of 1, we'll use 2. To test these means that we need to plug into the original polynomial inequality. So this one's going to be a little bit ugly by hand. So I've actually copied the tables from the graphing calculator to help us out just a bit. So if we were to plug in the negative 3, we would have negative 4 times negative 3 cubed minus 8 times negative 3 squared plus 4 times negative 3 plus 8. And we want to see if that's less than or equal to 0. So I input this function that we see on the left side of the inequality into my equation editor for y1, and then I went to the table. And so when I look at the x value of negative 3, I see an output value of 32. So that tells me that this expression is going to simplify to 32. Is that less than or equal to 0? No, that is false. And then we have to plug in negative 1.5 for region B. So I'd have negative 4 times negative 1.5 cubed minus 8 times negative 1.5 squared plus 4 times negative 1.5 plus 8. Is that less than or equal to 0? Well, to plug in negative 1.5 on your calculator and see it in the table, you would have to change your table setup so that your table starts at negative 2 and the change in your table is 0.5. And so whenever I did that at negative 1.5, I see an output value of negative 2.5. So is negative 2.5 less than or equal to 0? Yes, because that output value is negative there. And then when we plug in 0 in region C, Notice that all of the variable terms would just be 0. So negative 4 times 0 cubed minus 8 times 0 squared plus 4 times 0 plus 8. Is that less than or equal to 0? Well, I just get 8, but 8 is not less than or equal to 0, so that is false. And lastly, we'll plug in 2. We get negative 4 times 2 cubed minus 8 times 2 squared plus 4 times 2 plus 8. And we want to see if this is less than or equal to 0. Well, in my table, I can see that when x is 2, the output value is negative 48. So is negative 48 less than or equal to 0? Yes, that is true. And notice how these are alternating between false, true, false, true. And the previous problem did that too, either true, false, true, false, true, false. That will always happen unless there's an even multiplicity at one of the zeros. But here what I know is I'm trying to find all the values of x for which this function is negative or 0. Right, so all x for which f of x or y is negative or 0. Well, it's negative where the function tested true, which is in regions B and D. Now, because we're also permitted to equal 0, we can include our zeros in our solution set. So we're going to shade region B, which is everything between negative 2 and negative 1. Shade region D, which is everything to the right of 0. But we can put brackets on our endpoints to indicate those are included in our solution set. So in interval notation, our solution set is bracket negative 2 comma negative 1 bracket union bracket 1 to infinity. Now graphically, what could we do? Graphically, I know the function negative 4x cubed minus 8x squared plus 4x plus 8 is an odd degree function, right? Its degree is 3, which is odd. And the leading coefficient is equal to negative 4, which is negative. So I know from that that the graph goes down to the right. Remember, the leading coefficient tells me it's going to end, how it will end to the right. Because it's odd, it's going to do the opposite thing to the left, so it's going to go up to the left. And we also know that our zeros were negative 2, negative 1, and 1. So I can use this information to actually solve this problem without touching a calculator. I know that if I place my zeros of negative 2, negative 1, and 1 on my number line, I know that the graph has to go down to the right, which means to the right of this rightmost zero of 1, it's going to go down to the right. And I know that it's going to go up to the left. So to the left of negative 2, I know the graph has got to go up. Well, because each of my zeros have a multiplicity of 1, it's going to cross the x-axis. So it's going to be up to the left of negative 2, but then it's got to cross the axis and go down. And then it's got to come back up to go through this intercept of negative 1, 0. And then it's going to go up because it crosses there. And then it's got to go up and turn back down to be able to cross at the x-intercept of 1. And so I'm trying to find the values of x for which this function is negative or 0, and that means where the graph is below or on the x-axis. And so we know to the left of negative 2, it's above the x-axis. Between negative 2 and negative 1, it's below. Between negative 1 and 1, it's above. And to the right of 1, it's below. And so right there, I know my solution set because I can include the zeros is bracket -2 to -1, union bracket 1 to infinity. Now, if I wanted to graph it on my calculator and see the exact shape, I can certainly do that, but I get the same shape, right? That it's above to the left of -2, below between the -2 and 1, above between the -1 and 1, and then below to the right of 1. And I can also use my table to determine, if I need to, the sign of the y value in each of those intervals. This next one is 0.4 times x minus 1 times x plus 2 quantity squared is less than 0. And so this one is already in factored form. When I try to find my boundary numbers, I'm just going to set this equal to 0. So I get 0.4 times x minus 1 times x plus 2 quantity squared equals 0. And when I solve this, I just set those variable factors equal to 0. So I get x minus 1 is equal to 0, or x plus 2 squared is equal to 0. So we get that x is equal to 1, or x plus 2 squared equals 0 really gives me x plus 2 equals plus or minus the square root of 0, or plus or minus 0, which when I subtract 2, I really just get x equals -2. So note here that this 0 of -2 actually has a multiplicity of 2, and that will come into play in just a little bit. So I'm going to place the -2 and the 1 on my number line, and notice that it divides the number line into 3 regions. Region A is to the left of -2, so -infinity to -2. Region B is between the -2 and 1, so -2 to 1. And then region C is everything to the right of 1, which is 1 to infinity. So test point in region A would be something like -3. Test point in region B would be 0. And a test point in region C would be 2. So I'll plug these into the original inequality. 0.4 times -3 minus 1 times -3 plus 2 quantity squared is less than 0. And honestly, I don't really need to know the exact value. I just need to know, is that expression less than 0 or not? And notice that I would get 0.4 times -4 times -1, but I square it, and -1 squared is 1, is less than 0. So a positive times a positive is actually negative. Now, if you wanted to use your calculator and look at the output values on the table, you can. Like if I plug in -3, my output value is -1.6. But notice that it's negative, and is that less than 0? Yes, so that is true. If we plug in 0, 0.4 times 0 minus 1 times 0 plus 2 quantity squared, is that less than 0? Well, when I plug in 0 on my calculator, I see that the output value is, again, a -1.6. Is that less than 0? Yes, that is true. And then in region C, if we plug in 2, we get 0.4 times 2 minus 1 times 2 plus 2 quantity squared. Is that less than 0? Well, when we plug in 2, the output is 6.4, but 6.4 is not less than 0, so that is false. So notice that our regions are testing true, true, false. They didn't alternate, and that is because of this even multiplicity on the 0 of -2. So around the -2, the intervals will test in the same way rather than alternating, because remember, it has that effect of bouncing off the axis, which means it's either going to both be above or both be below. And so we want to shade the regions that tested true. That is, those are the regions that contained x values which make the output negative, and that is in region A and region B. So notice that we have two intervals right next to each other that are shading true. But I need to think about, do I get to include the endpoint? And this is where it's strictly less than 0, so I cannot include the boundary numbers, which I indicate with the parentheses. So because -2 separates the two regions that tested true, I have to have a parentheses facing to the left of -2, and also a parentheses facing to the right of -2, and then a parentheses on -1. So my solution set is -infinity to -2, parentheses, union, -2 to 1, all with parentheses. Now, graphically, what would I do? Graphically, I just realized that, my function f of x is this 0.4 times x minus 1 times x plus 2 squared. It has a degree of 3, which is odd. And its leading coefficient, if I expanded all of that, would just be 0.4, which is positive. So this tells me that the graph is going to go up to the right and left. It will go down. But I also know that my zeros were 1 and -2, but -2 had a multiplicity of 2, right? It's even. 1 had a multiplicity of 1, so it's going to cross at the 0 of 1, but it will bounce off at the 0 of -2. So whenever I put all of that together, I'm going to plot my two x-intercepts of -2 and 1, and then let's think about the end behavior. We know it's going to go up to the right, so that means up to the right of this rightmost 0, so it's going to go up to the right of 1. It will go down to the left, so at -2 it's going to go down to the left of that. Now because the graph bounces off at -2, it's also going to go down to the right of -2, but then it's going to go down to some point and it has to turn back up to be able to go through and cross at the 1, 0. So again, graphically I see I'm trying to find the values for which the output is negative, or where the graph is below the x-axis, and that is to the left of -2 and also between the -2 and -1. And so right there I would know my solution set is -infinity to -2, parentheses, union, parentheses, -2 to 1, close parentheses. Now again, if you don't want to graph by hand, you could use your calculator, sketch the graph by inputting this function into y1, and you can see the same behavior that we just found. Okay, now we want to solve the problem. The value of Emily's stock portfolio is given by the function v of, it should be v of t, is equal to 50 plus 69t minus 3t squared, where v is the value of the portfolio in hundreds of dollars and t is time in months. When will the value of Emily's portfolio be over $41,000? So we want to solve an inequality. Keep in mind that our output value is in hundreds of dollars, so 41,000, if we divide by 100, we actually get 410. So we really want to find when 50 plus 69t minus 3t squared is greater than 410. So to solve that inequality, we want to first set it opposite from 0. We can subtract 410 from each side, so we get -3t squared plus 69t minus 360 is greater than 0. So we can solve it by first finding the boundary numbers, by solving this associated equation, -3t squared plus 69t minus 360 equals 0. We can divide through by this common factor of -3, and that will give us t squared minus 23t plus 120 equals 0. So when we factor this, we need the factors of 120, whose sum is 23, and that is 8 and 15. And both of them will be negative, so t minus 8 times t minus 15 equals 0. So we get zeros of 8 or 15. And when we place these zeros on the number line, 8 and 15, we get 3 regions. Our region A is the interval from -infinity to 8. Region B is between 8 and 15. And region C is 15 to infinity. Now we can use a graphing calculator to help us figure out how this inequality will be tested true or false. So in region A, our interval -8 to infinity, if 0 is in the interval, I say use that as a test point. So we'll put in t equals 0. In region B, we can say t is equal to 9. In region C, something larger than 15, so we'll use 16. And I'm plugging into this original inequality -3t squared plus 69t minus 360 to determine if it's greater than 0. So that would give me -3 times 0 squared plus 69 times 0 minus 360. Is that greater than 0? Well, no, that gives me just -360, which is not greater than 0, so it is false there. And I could also see that because to the left of -8, the graph goes down. Now my new graph that I have on the screen goes from 0 to 20 and counts by 2s, and 0 to 100 and counts by 10s. And so we can see it crosses at 8 and 15, and to the left of the 8, the graph is down. Between the 8 and the 15, the graph is up above the axis, and to the right of 15, it's below the axis. But we can also see that through these test points algebraically. Right, when we plug in 9, -3 times 9 squared plus 69 times 9 minus 360, is that greater than 0? Well, if we plug in 9, we'll get this output value of 18, which is greater than 0, so that is true. And then if we plug in 16, -3 times 16 squared plus 69 times 16 minus 360, is that greater than 0? Well, when we plug in 16, the output is -24, and -24 is not greater than 0, so that is false. And again, I would have known, once I know the first region is false, and I have odd multiplicities on my zeros, it will alternate false, true, false. But I can see that graphically, because the only place the graph is above the x-axis is between the 8 and 15, or in region B. So I shade the interval between 8 and 15. I cannot include my endpoints because I want to find when it's strictly greater than the 41,000. So my solution set in interval notation is parentheses 8 to 15. But in words, when will the value of Emily's portfolio be over 41,000? And that will be between 8 and 15 months.